sorry for the delay. I don't know, I was not able to record the video, that's the reason. Fine, so today I'm going to discuss about induction motor starting. That means to say, how does an induction motor start automatically? Alright. So the operation, what I have done is I have broken down the operation into 8 parts. So basically, this is the sequence of events taking place when you connect an induction motor to a 3-phase AC supply. Okay. Now, this is the symbolic representation. What you have is a stator, and inside the motor you have a rotor. It is assumed that when you are about to start an induction motor, the motor is under rest. That means to say the rotor speed Nr is equal to 0 RPM. So Nr is equal to rotor speed. Rotor speed. Okay. Alright. So when a 3-phase AC supply is connected to the stator winding, when a 3-phase AC supply is connected to stator winding, a rotating magnetic field is produced in the area. This rotating magnetic field will rotate at synchronous speed, and the synchronous speed is given as Ns is equal to 120 F by P. This rotating magnetic field constantly rotates in the air gap between stator and rotor. Initially, rotor is under rest. That means to say, rotor speed is 0. So what happens is that the rotating magnetic field is going to cut the stationary rotor, due to which an EMF is induced in the rotor. Now, rotor is a short circuit one, right? Either it is short circuited by means of squirrel cage rotor, or it is short circuited by means of slip ring induction motor. So, in the short circuited rotor, the induced EMF will circulate current. Correct? Because circuit is closed, so the induced EMF in the rotor can circulate current. So the moment when the current start flowing into the rotor, we can say that when a current carrying conductor is placed in a magnetic field, experiences a force, and that force basically acts on the outer periphery of the rotor. So rotor is always a circular circuit, right? So this is how the force component is going to be acting on the outer periphery. Okay. So all these forces basically acts tangentially to the rotor surface, due to which torque is produced, and due to the production of torque, the motor starts rotating. Alright, so this is the working or operation of induction motor. Alright, so quickly let me brief up. 3-phase AC supply is connected to the stator winding, due to which rotating magnetic field is produced. The rotating magnetic field rotates at synchronous speed, which is 120 F by P. Initially, the rotor is at rest, so the rotating magnetic field is going to cut the stationary rotor conductor, due to which an EMF gets induced in the rotor. Rotor is a closed circuit, hence currents are start flowing into the rotor circuit. Whenever a current carrying conductor placed in a magnetic field experiences a force, and this force is acting tangentially on the rotor surface, due to which a torque is produced, and due to the production of torque, the motor starts to rotate. Okay. So this is the working principle of induction motor. Okay. For 6 to 8 marks, they can consider. Alright. Now, somewhere we have spoken about induction of EMF in rotor. Alright. So, due to the production of rotating magnetic field, EMF gets induced in rotor. Right? Because to induce EMF, either you should have the conductor moving, or you should have the magnetic field moving in nature. Alright. So the EMF gets induced in the rotor. Now, as per Lenz's law, the induced EMF, it opposes the cause. Now, in the three-phase induction motor, the cause is nothing but the relative speed. Cause is relative speed between RMF and rotor. Relative speed between rotating magnetic field and rotor. Now, what is the speed of rotating magnetic field? Is ns. And what is the speed of rotor? Is nr. So, the relative speed or the difference in speed between rotating magnetic field and rotor is given by ns minus nr. ns minus nr. So, this induced EMF always tries to oppose this relative speed. That's because if relative speed exists, there will be an induction of EMF. If the relative speed ceases to 0, then there will not be any production of EMF. Alright. So this is the cause for the production of EMF. Alright. Now, based on this relative speed, you can derive a very important relation in an induction motor. Alright. So next up, you have the derivation of frequency of induced EMF. Next you consider derivation of frequency of induced EMF in rotor. Now, to derive an expression for frequency of induced EMF in a rotor, what we have to do is we have to consider the two frequencies. One frequency is related to the stator frequency or the frequency of rotating magnetic field, and the other frequency is related to the frequency of the rotor. Alright. Now, let us start by mentioning speed of rotating magnetic field. Okay. So first let us write an expression for speed of rotating magnetic field, which is ns is equal to 120 f divided by p, where f is equal to source or supply frequency, okay, and p is equal to number of poles. Okay. All right. Let us consider this expression as 1. Similarly, you can also write an expression for relative speed, right? Because when it comes to rotor, it is not that you have only rotor speed, you have the relative speed, because if there is a speed difference, there will be change in flux. Alright, so with respect to rotor, relative speed, that is ns minus nr, can be given as 120 fr divided by p. Now, what is this fr? Fr is where fr is equal to frequency of rotor. Okay, frequency of rotor. When you say frequency of rotor, what I meant to say is the frequency of rotor induced EMF and rotor induced current. Okay. So that's your second equation. Now let us say equation 2 divided by equation 1. Let us divide the two equations. Okay. So equation 2 divided by equation 1. So ns minus nr divided by ns is equal to 120 Fr by P into P divided by 120 here. So PP 120 gets cancelled. So you are left with Fr divided by here. You are left with Fr divided by here. So that implies, okay, you can cross multiply. Fr is equal to, that implies Fr is equal to F into ns minus nr divided by ns. Ns minus nr divided by ns. Now, the ratio ns minus nr divided by ns, does it have any dimension? It is not having any dimension, right? In the sense, ns minus nr is expressed in RPM. And ns is also expressed in RPM. So RPM gets cancelled. So basically, you will get Fr is equal to, the unit of Fr remains Hertz. Okay. Now, the ratio ns minus nr divided by ns is called as slip of the induction motor. And so you can write Fr is equal to slip times the frequency of the supply. Okay. So let me write it here. The induced EMF, the frequency of induced EMF or current in rotor is taken as Fr, and Fr is equal to slip times the supply frequency there. So expression for rotor frequency is Fr, and that is equal to slip times SF. Slip times here. So this is a very small derivation. Okay. For 6 to 8 marks, this derivation may come. Okay. Expression for Fr. So Fr is equal to slip times supply frequency. Next you write something like effect of slip on Fr. That is slip effect on frequency of rotor induced EMF. Okay. So we have slip is equal to ns minus nr divided by ns. Okay. Now, let us consider different cases. Okay. Carefully observe. Okay. First, let us consider at standstill condition. Standstill condition. Okay. It's a, what do you say, standard term used in electric machine industry. Okay, standstill condition. Standstill or still condition means no rotation, right? Still means no movement, so no rotation. What do you mean by no rotation? No rotation means nr is equal to 0. That means to say the motor is not at all rotating. So speed of the rotor is 0. Okay. Now what do you mean by 0 RPM? What happens to slip? So when there is no rotation, slip S becomes ns minus 0 divided by ns is equal to 1. So slip becomes 1. So this is very, very important. Okay. So the other way of asking the question is something like this. When do you get unity slip? You get unity slip when the rotor speed is 0. And this particular condition is called as standstill condition. Okay. So you can highlight S is equal to 1 condition. Now, when you get S is equal to 1, what happens to Fr? We have Fr is equal to S into F. Right? I hope you are not confused with Fr and F. So this F refers to supply frequency. Okay. Supply frequency is nothing but your 50 Hz frequency. Okay. And Fr refers to rotor frequency. Rotor frequency. So when you get S is equal to 1, Fr is equal to F. So rotor frequency is equal to the stator frequency. Rotor frequency is equal to stator frequency. Okay, so let's say this is your case 1. Now let us consider case 2. Wherein let us consider NR is less than ENS. Let us assume that rotor is running at a particular speed such that the rotor speed is less than the synchronous speed. So when NR is less than NS, so what happens to slip? So slip is given as NS minus NR divided by NS. So when NR is less than NS, so you will get slip value less than unity. You get slip value less than unity. Okay. So this condition is always called as motoring operation. Motoring operation. Okay. In the sense, the given induction machine operates as a motor, an induction motor. Okay. So for a motoring operation, the slip value is always less than unity. It is greater than 0 but less than unity. Okay. Fine. Now, what implication it has on the frequency? Once again, let us write the frequency expression Fr as slip times F. So slip is less than unity, due to which Fr is always less than F. Okay. So frequency of rotor induced EMF is always less compared to the frequency of supply. Okay. And this condition you will get only for motoring operation. Alright. So that's your second case. Okay. Now let us consider the third case. Okay. So in third case, let us say Ns is equal to Nr. What we are assuming is that the speed of the rotating magnetic field is equal to the speed of the rotor. What happens during that condition? So S is given as Ns minus Nr divided by Ns. So Ns is equal to Nr, right? So Ns minus Ns divided by Ns. So 0 by Ns is equal to 0. So slip becomes 0. Okay. Slip becomes 0. When slip becomes 0, what happens to Fr? The rotor frequency Fr is given as slip times F is equal to 0 into F is equal to 0 hertz. What do you mean by 0 hertz? 0 hertz means there is no induced EMF in rotor. You can say something like the signal is dead. And why the signal is dead? Because there is no relative speed. If there is no relative speed, the rotor frequency becomes 0, and 0 frequency means there is no EMF in the rotor. Okay. So that is the reason I was telling in the beginning. Okay, that if you have to have any rotations, you have to have some relative speed. So if you force the rotor to rotate at synchronous speed such that ns is equal to nr, the slip becomes 0, due to which the frequency becomes 0. Okay. Now, when the frequency becomes 0, what happens? The rotor stops, right? Because there is no frequency, no EMF, no torque. When torque becomes 0, the motor stops. Or you can say rotor stops. Once the rotor stops, will there be any relative speed? Yes, there will be relative speed, because relative speed is ns minus nr. So the moment the rotor stops, nr becomes 0, hence the relative speed becomes ns. So once again, the motor starts rotating. And when it again touches the synchronous speed, again the slip becomes 0 and the rotor frequency becomes 0. So the motor kind of gets into start, stop, and then again it starts, and then again it stops, so on and so forth. Which is highly objectionable, right? Because we don't want our ceiling fan to get into this start-stop situation. Because if it gets into start-stop situation, what happens? You will not get any useful operation from it, right? So this condition needs to be avoided. But will it happen in a physical machine? No, it won't happen in a physical machine. That's because your rotor will have certain moment of inertia, right? Because rotor is consisting of windings, and once again your rotor is fitted with a shaft, etc., etc. So due to which there will be a considerable amount of moment of inertia present in your rotor. So due to this moment of inertia, or J, what happens is that in all practical machines, the rotor speed is always less than the synchronous speed. The rotor speed is always less than the synchronous speed. And why is that so? It is due to the moment of inertia J of the rotor. Okay. So luckily we don't face such a problem in our day-to-day life. That's because rotor has some weight in it, right? So due to that weight, your rotor always falls behind the rotating magnetic field. Okay. Nevertheless, theoretically you can carry out an assessment. What if the rotor speed is equal to the stator speed? What happens? Frequency becomes 0, due to which rotor stops. The moment rotor stops, there will be a relative speed. And due to the relative speed, the motor once again starts. And once again, when it reaches synchronous speed, it stops, then starts, and then stops. Highly objectionable operation, but due to the moment of inertia, luckily we are not seeing this particular behavior in our day-to-day life. That's because every motor will have some amount of moment of inertia. Nevertheless, pretty interesting property, right? What if the rotor catches up with the stator field? So 3 conditions we looked at, right? The fourth condition, last condition. What if somehow we succeed in achieving the speed of the rotor greater than the synchronous speed? So I am putting this condition. What if we succeed in accelerating the rotor at a speed greater than the synchronous speed? Now the question is it possible practically? Yes, it is possible. Okay, let me show you the setup also. Let's say this is your induction machine. I won't call induction motor, I would say induction machine. Okay. So let me write. Let's say this is our induction machine. And let's say this is your shaft. Let us connect this shaft to a prime mover. Okay. So this is your prime mover. Okay. Example for any prime mover, can you give me? Say for example, IC engine, internal combustion engine. IC engine. And let us also define, okay, let us say that the synchronous speed of this particular induction machine is 1500 RPM. Okay. The synchronous speed of this particular induction machine is 1500 RPM. Okay. Now, what we can do over here is that, let's say we start this IC engine, let us say at 2000 RPM. Possible, right? Because this is an independent circuit. Okay. Either you have to use petrol or diesel as the fuel. So the moment when you turn on a particular IC engine, your IC engine starts to rotate at a particular speed. Let's say that speed is 2000 RPM, and the synchronous speed of the machine is 1000 RPM. So what is happening basically? So this IC engine or the prime mover is directly coupled to this particular induction machine via shaft. So when the IC engine is running at 2500 RPM, what happens to the rotor speed? The rotor will also be rotating at the same speed. Why it rotates at the same speed? Because it is directly coupled, right? So when this rotates at 2000 RPM, the rotor also rotating at 2000 RPM. Now you compare the NS value with NR. NR is greater than NS. So this is what it is done while producing electricity. So basically what is happening over here is that the mechanical energy is overpowering the electrical energy. So mechanical rotations are overpowering the electrical rotation because NS is produced when you connect electric supply to the stator winding of an induction motor, right? RMF is produced when stator is connected to electric supply. But in this case, what is happening? The rotor is rotating at 2000 RPM, which is much greater, in comparison with the NS. Okay. So this particular operation is called as generator operation. Generator operation in which the mechanical energy is overpowering electrical energy. So what happens if you give the input as mechanical energy? You will get electrical energy as the output. Okay. So that is what is happening in case number 4. So whenever your rotor speed is greater than the synchronous speed, the induction machine gets into generator operation. Okay. Now, when it gets into generator operation, what happens to slip? Slip is given as Ns minus Nr divided by Ns. But Nr is greater than Ns, so slip is negative. Okay. Or you can say slip is less than 0. Okay. So negative slip is an indication of generating operation. So you can say that it is generating mode, right? So in case 2, if you recall, I had mentioned about motoring mode. So the same machine can be operated as a motor or the same machine can be operated as a generator. So when slip is negative, what happens to Fr? Fr is S times F. So as S is negative, you will get Fr is equal to negative hertz. But frequency we always consider it as a scalar quantity, right? 50 hertz, 60 hertz. We never say minus 50 hertz cycle or plus or minus 100 hertz cycle. Okay. So same thing over here also. The negative slip value is a mere indication of the power reversal. That means to say, instead of converting electrical energy into mechanical energy, what is happening is the machine is converting the mechanical energy into electrical energy. Okay. So negative slip simply relates that the machine is operating in generating mode. The machine is operating in generating mode. Alright. So this is a very interesting discussion on effect of slip on FR. Okay, effect of slip on FR. So as a summary, okay, what we can do is we can write, say, a case. Let's say case number 1, 2, 3, 4, and we can mention about status of speed NR, and then we can talk about slip, that is ns minus nr divided by ns, and here you can write about Fr is equal to F into S, and here you can write something like comments. So case 1, let us consider NR. See, speed of status of speed NR. NR is equal to 0. If NR is equal to 0, slip is equal to 1. When slip is equal to 1, Fr is equal to F. Okay. So in comments you can write stator and rotor frequency is the same. Now let us assume that status of NR is such that NR is less than the synchronous speed. So when rotor speed is less than synchronous speed, the slip value is greater than 0 but less than unity. Slip value is greater than 0 but less than unity, because unity you will get only when NR is equal to 0. So due to which the rotor frequency Fr is less than the stator frequency F. And what do you call this particular operation where the rotor speed is less than stator speed? This particular operation is called as motoring mode. This particular operation is called as motoring mode. Okay, alright. So third condition, crazy condition, you could say NR is equal to NS. What happens by chance, the rotor speed becomes equal to the stator speed. When NR is equal to NS, slip becomes 0, due to which Fr becomes 0. That means to say the frequency of induced EMF of rotor is 0, and motor stops and then starts and then stops, so on and so forth. Okay, so this I want to highlight. Okay, so this particular question they will ask for, let's say, short notes for 4 marks. What will happen if the rotor speed matches with the synchronous speed? I think I have already explained. I don't want to bore you by telling these things again and again. So what happens? Slip becomes 0, due to which induced EMF in the rotor winding becomes 0. When there is no induced EMF in the rotor winding, current will be 0. If current is 0, then there will be no force produced in the rotor. If there is no force, no torque, and due to 0 torque, the motor stops. The moment the motor stops, there exists relative speed, because relative speed is ns minus nr. When nr is 0, you get maximum relative speed. Once again the motor starts to rotate. But once again, when the motor catches catches up, the speed of the motor becomes equal to stator, again it gets into the same mode. Okay. So that's right. Finally, you have NR greater than NS. If NR is greater than NS, then slip is basically less than 0 or negative. Less than 0 is negative. When slip is negative, FR is negative. What is the indication? The indication is that the machine is operating in generating mode. Machine is operating in generating mode. So this